We're in Rosen section 3.2, continuing our discussion of big O notation, and we're going to use the definition of big O in two different ways. Here we have another proof to show that one function is big O of another function. Here, 7x squared, we're going to show is big O of x cubed, and we will use the assumption, we'll fix k and show that we can find a c. So we'll fix k to be 7. So x is greater than 7. If I multiply both sides by x squared, I get 7x squared is less than x3, and x3 is the object of our big O, which has a coefficient of 1. So when k is equal to 7, then c is equal to 1. And we've shown that 7x squared is big O of x cubed. And I will let you determine if you can see if c equal 7 and k equal 1 work. So you'll fix k to be 1 and then show whether c equals 7 is a witness. All right, I want to use it a different way. Now I want to use the definition to show that something is not big O of another function. Here we have n squared, and I'm going to show that it is not big O of n. Clearly n squared grows faster than n, but perhaps there's a constant multiplied by n which would allow it to be faster than n squared. Well, we'll show that that's not the case. When we suspect that one function is not big O of another, the typical approach is to assume that it is. So here's our approach. We're going to assume that there are constants c and k, for which n squared is less than or equal to cn, that's the definition of big O, whenever n is greater than k, there's the two witnesses. And then we'll use those two portions of the definition to show a contradiction. We will divide both sides of n squared less than or equal to cn by n to get n is less than or equal to c. But remember, n it has to be true for any n greater than k. There cannot be an upper bound on n. So there's a contradiction when we say n has to be less than or equal to c whenever n is any number greater than k. So this is how you can show a function is not big O of another function. In particular, we have a way to describe the big O immediately for polynomials. And we'll see that here. If I have f of x is a polynomial of degree n, so the highest order term is a sub n times x to the n, and we'll show that the polynomial is big O of x to the n, the order of the exponent of the highest order term. Here's our proof. We'll take the absolute value of both sides, and note then that if we have the sum, the absolute value of a sum of terms here, well, by the triangle inequality, that is less than or equal to the sum of the absolute values of those terms. And now I can factor out x to the n right here, leaving me with the coefficients divided by x raised to various powers. Now if x is greater than or equal to 1, this will be strictly less than or equal to x to the n times the sum of those coefficients, absolute values of. And that gives us a constant that says f of x is less than or equal to x to the n times that sum. So if we take c to be the sum of the absolute values of the coefficients and k to be 1, then f of x there's witnesses that f of x is big O of x to the n. As I said, the leading term or the highest order term of the polynomial dominates its growth. Let's look at a couple of other functions that are pretty typical. This one is very typical. We're going to be looking at the sum of the first n integers. What is the big O of that? Well, we'll do creative replacement, and we'll replace every term by n, since that is always less or greater than or equal to that term. Well, if I do that, then I have n of those, which gives me n squared. So the sum of 1 to n is going to be big O of n squared, with c equal 1 and k equal 1. What about the product of the first n integers? Well, that's the n factorial. And I can do creative replacement there. I'll replace 1 with n, 2 with n, because n is always greater than or equal to those terms. And I have n multiplied by itself n times to give me n to the n. So n factorial is big O of n to the n, with c of 1 and k of 1. And then finally, we'll look at the big O estimate of log of n factorial. Well, n factorial is less than or equal to n to the n, so log of n factorial is going to be less than or equal to n times log of n. If I take log of n to the n, I can bring the exponent out to be a multiplier. And that is some other uses of the definition of big O.